Okay, so I'm going to do a review video here. So the calculus-based test, so there won't be any calculus-based final. Everything's being covered on this test. So, one-dimensional motion. So what we're talking about here is we're given, just check something here, test problems. Yeah, okay, so there's a one-dimensional motion problem. And you're going to be given x as a function of time. So what I'll do is I'll give you a equation for x as a function of time. So, in constant acceleration motion, the acceleration is a quadratic. If you have variable acceleration, it could be a third-order polynomial. So, it's going to be something like a plus bx or pbt plus ct squared plus dt cubed, something like that, possibly. I won't go any more than that. And I'm going to ask you to calculate, I could ask you to calculate the velocity as a function of time. And all you have to do there is take the derivative of x with respect to time. So you'll come up with a polynomial. If you wanted the acceleration, you could take the derivative of the velocity with respect to time, or you could take the second derivative of the position with respect to time. So that's just a matter of doing simple derivatives. Now, if I asked you to find the average velocity over a time period, from t1 to t2, what you would do there is you would find the position at t2 and subtract the position at t1 and divide by t2 minus t1. So that is the average velocity. Now, there's also the average velocity where you would integrate the velocity and then evaluate the integral, which wouldn't be exactly the same thing. So this is the average velocity. The other way you would do it is you could take 1 over t2 minus t1 times the integral from t1 to t2 of v of t dt. So that's another way you can come up with the average velocity. But if I ask for average velocity, I'm asking you to do that. So you'd have two times. You can plug that into your position function of time, get the two values, subtract them, divide by the difference. For constant acceleration motion, these are going to be, the average velocity is going to be the same, calculated both ways. But if you had, say, acceleration that was linear, or you had a third-order polynomial like this, they're not going to be the same. Okay. So this equation, by taking the derivative of this function, plugging it in, gives you the instantaneous velocity. So if I am asking for the instantaneous, you use the derivative. If you're looking for the average velocity, you take the instantaneous position, take the difference divided by that. Okay, so that's one kind of problem. Now, in two-dimensional motion, what you're talking about there is, there's two ways of doing this. You could have x as a function of t and y as a function of t, and those could be polynomials of any kind. Or you could do it r as a function of t, and that would be x as a function of t times the unit vector I plus y as a function of t times the j unit vector. So these are just two ways that you could represent two-dimensional motion. You could look at them in component form as a function of time, or you could put them into a vector form. So, if you wanted to find the velocity vector as a function of time, all you have to do is take the derivative of the components with respect to time times the corresponding unit vector. In the same way here, if you wanted to find the acceleration as a function of time in 2 dimensions, you just do them separately. So here you can take the derivative. Well, actually, what you want to do here is you would want to take the second derivative, because this would be, let me just write this out here. What we have here is you have v sub x of t I plus v sub y of t j. So if you were to calculate the acceleration, there's two ways you can do it. You can take the second derivative of x as a function of t with respect to time I plus the second derivative of y of t with respect to time times j, or you could go from the velocity vector, so that would be the derivative of v sub x of t with respect to time plus the derivative of v sub y with respect to time times j. So those will give you the same answers. So if I give you a two-dimensional problem, again, a polynomial of some kind, you just have to do simple polynomial differentiation to get the velocity and the acceleration. Now remember, if I asked you to find the magnitude and direction of the velocity, say, the magnitude direction of the velocity at a given time, you would, these give you the components. So to find the magnitude of the velocity vector at some time, you take v sub x of t squared plus v sub y of t squared, take the square root of it. So that gives you the magnitude. And the direction would be the inverse tangent of v sub y of t divided by v sub x of t. So let me just give you an example. So let's say you have 5t plus 3t cubed as the x component of the position. And then you have the y, let's say it's negative t squared plus t to the fourth. Okay, so those are the positions. So how would I write that as an r vector? It would be 5t plus 3t cubed I plus negative t squared plus t to the fourth j. So that would be the position vector. So if I want to find v sub x of t, I would take the derivative of this part. So I'd get 5 plus 9t squared, and v sub y of t is going to be equal to negative 2t plus 4t cubed. So those would be the components. So this is the x component of the position, this is the y component of the position. So you just take the derivatives. The velocity vector as a function of time would be equal to 5 plus 9t squared I plus negative 2t plus 4t cubed j. So that would be the velocity vector. And then if I wanted to do the acceleration vector, it's going to be equal to, we take the derivative again, so that would be 18ti plus negative 2 plus 12t squared j. So that would be your acceleration vector as a function of time. If I said, what is the magnitude and direction of v vector at t equals 2 seconds? Well, then you just plug that in to here. So you get 5 plus 9, 2 squared I plus negative 2 times 2 plus 4 times 2 cubed j. So the velocity vector at t equals 2 is going to be what? That's 4 times 9 is 36 plus 5 is 41i. And here we have 2 cubed, which is 8, times 3 times 4, which is 32, minus 4, which is 28. So plus 28j. So that is the velocity vector at a particular time t. And then if I wanted the magnitude of v at the 2, you take 41 squared plus 28 squared, take the square root of that. 41 squared plus 28 squared, square root. You get the magnitude of v is 49.6, say meters per second. Assume the units over here are meters. Okay, so that would give you the magnitude, and the angle theta would be the inverse tangent of v sub y, which is 28 over v sub x, which is 41. Make sure you have calculators in degrees. So we take the inverse tangent, 28 divided by 41, and we get 34.3 degrees. Okay, so that's what I'm talking about here as far as being given two-dimensional motion. You're given the position as both x and y positions as a function of time. And the velocities are the derivatives of the components. Okay. Now, so those are where you're given position, and you have to calculate velocity and acceleration. The opposite way is I give you acceleration as a function of time. So, the simplest case would be one-dimensional motion. So I could give you, if it was just a constant, we know what those results are. But if let's say you had 3t, and we could put an I, and that would be one-dimensional motion if that was all there was to it. Or I could leave off the I and just assume it's one-dimensional motion. So what I'd ask you to do is find the velocity and position as a function of time, given I have to give you some initial conditions. So v of 0 is, say, negative 2 meters per second, and x of 0 equals 12 meters. So I'll give you the acceleration, the velocity, and the initial velocity, initial position. So the velocity is going to be equal to the integral of the acceleration with respect to time. So this is like the indeterminate, not indeterminate, but improper indefinite integrals, I guess that's what they call them. So you plug, your expression into here like that, and then you integrate. So you get 3t squared over 2 plus c, and then you could use your initial condition to find c. So in this case, because they're all at t equals 0 and we're dealing with polynomials, c is always that. So this is our general solution. Then we can add do c, okay? So at t equals 0, v is negative 2. And then you can integrate to find the position as a function of time. You integrate the velocity. So you'd end up with, so you get t cubed over 3. Those 3's would cancel out. So you'd end up t cubed over 2. Here we just get 2t. And we'd have an arbitrary constant c again. But, our initial position is 12 meters. So c would end up being 12 meters using our initial conditions. And in this case, the initial conditions are almost always at t equals 0, so it's easy to find c. And so that is now your position as a function of time. So you give an acceleration, you have to use integration to find velocity, and you have to use integration plus initial conditions to be able to find velocity and position. Now in 2 dimensions, you'd have a sub x of t is equal to, let's say, t, and a sub y of t is 3. How would you do that? Well, you would have an acceleration vector, which would be ti plus 3j. So that's the acceleration vector. And in addition, you'd have to say v sub x of 0 equals, say, 1, and v sub y of 0 equals 2. So those are my y velocity initial conditions. And when you integrate this, when you integrate the acceleration vector, you integrate each component separately. So here you get t squared over 2i plus 3tj plus you'd have a c1i plus c2j. So you have two initial condition vectors. So you would do these in component form. Again, what you'd find out is because these are at 0, c sub c1 would be 1 and c2 would be 2. So applying these initial conditions, you'd end up with t squared over 2 plus 1 from here, whole thing times I plus 3t plus 2 times j. So that's your velocity vector as a function of time. Then to find the position as a function of time, you'd have to have x of 0 is something, and y of 0 is something. So you'd have to have both initial conditions for the position. So when you got the position vector as a function of time, you'd integrate this stuff. So what would happen is you'd get, here you get t cubed over 6 plus t times I, and when you integrate this, you get 3t squared over 2 plus 2tj. And then you have plus c1i plus c2j. And then you can apply the initial conditions, again, because they're evaluated at 0. You get t cubed over 6 plus t minus 2 from here, I plus 3t squared over 2 plus 2t plus 3j. As you can see, if I set t equal to 0, I get negative 2, positive 3, which are what the initial conditions are. So that's how you would do it in two-dimensional scenario. Okay. As far as torques and things like that are concerned, all I'm going to ask you to do is to be able to do a cross product. So I'll give you some kind of vector. Let's say it's I minus 5j plus 3k, and vector b is 2I plus 2j minus 1k, just minus k. So what I ask you to do is find the cross product. So remember what you do is you do I, j, k, 1, negative 5, 3, 2, 2, negative 1 in this matrix form. And then you find the determinant. So you can see I've got straight lines here. So you find the determinant. So you take I, this one, times this determinant of this sub part. It's called a cofactor. Then you have minus j. So you cross that row and that column out. You'd have 1, 3, 2, negative 1, plus k. Cross that row and that column out. You're left with 1, negative 5, 2, 2. And then you can multiply these out. So you get 5 minus 6 is negative 1. Here we get negative 1 minus 6, which is negative 7. With the negative sign, so that becomes plus 7j. Here we have 2 minus a negative 10, so that's 12 plus 12k. So that is how you do the cross product. And that's needed if you're calculating torques. So, this could be my R vector, and this could be my force vector instead of A and B. And to find the torque vector, it's just R cross F. So you can, even though you might say, oh, you're just doing a cross product here, it's really, the main reason for right now is to figure out the torque vector. And if you take statics, you'll see a lot of that. Okay. Another thing is that we said that the work as a function of x is equal to the the work done by an object is equal to the integral of force dotted with dx. So we're just going to look at one-dimensional motion. So the dot product just becomes a multiplication. And you can almost take the vectors off. Now, if you were doing this, you'd have to have x as a function of time. So how would you do that if this actually was something that was not just in one dimension? This is not the x vector, really. I guess it would be the r vector, the actual position of the thing. So what you'd have to do is you'd have to have the position as a function of time, and then you'd have to have the force as a function of time, and you'd have to do this dot product thing. But that's a little complicated, so we're not worried about this. We're just worried about how would you handle a force that is not a function of, is not just constant. Most of the cases we looked at, force is constant, except for spring, when we were calculating energy work done during compression of the spring, but all the other ones we talked about constant force. So, what kind of problem? You're just going to be given F as a function of X. So, it could be, and it's going to be just a simple polynomial. So if I asked you to calculate the work, all you'd have to do is do the integral of 5 plus 6x plus 7x squared times dx. And, you would, this would be from some initial x initial to some x final. So you'd integrate this. So you get 5x plus, let's assume it goes from 0 to 2 meters. So let's not integrate it yet. So to get the answer here, it's just a definite integral. And you can simplify this down to just 3. So if I asked you what is the work done, if the work is a function of position, is this, you would just plug in the upper limit and subtract the lower limit, which in this case is 0. But if it wasn't 0, then you'd have to plug that in. So it's just a simple definite integral. Okay. Just see if there's anything new here. Next problem that I have. Yeah, the only thing is, let's see if I've got this. Let me just put, it's the same basic idea. Yeah, I did it here. Okay. So two problems are similar to each other. And the final thing is just some vector math. So what I'll do is I'll give you two vectors. Let's say here, let's say v1, and we'll say v1 is equal to, so this is the velocity vector. We want to add velocity vectors or subtract velocity vectors. And this is a two-dimensional vector. So v1 vector, initial vector, let's say is just 5i minus 2j. And then my final velocity vector is v2. And so that's going to be, let's say, 3i plus 4j. So I'm trying to draw it somewhat to scale. And what might I ask you about these two vectors? Well, I might ask you what the magnitude of the vector is. So there, you would just take 5 squared plus negative 2 squared, take the square root. If I asked you for the magnitude of vector 2, that would be equal to the square root of 3 squared plus 4 squared, which is 5. This one is going to be the square root of 29. So those are magnitudes. In terms of directions, what I would do is this would be a negative angle, this would be a positive angle. So you could say theta 1 would be the inverse tangent of v sub y, which is negative, so it would be negative 2 over 5, whatever that is, and theta 2 would be the inverse tangent of 4/3. Make sure your calculator is in degrees. And then the final thing I would ask you is tell me something about the resultant. So the resultant is, going to look like that. So we'll call that v sub r. So how do we find v sub r given the two components? Well, v sub r, you just add the components together. So that's going to be 8i plus 2j. So that's the resultant vector by adding the components. You can kind of see that here. It's slightly positive, more x or in the x direction. And then if I asked you for the magnitude of the resultant vector, you just, again, 8 squared plus 2 squared, square root of 68. And if I wanted the difference between the two vectors, which, we did do that. We did that mathematically for when we were talking about centripetal acceleration. But if I wanted to say v2 minus v1, how would I do that? Well, you just subtract the components here again. So you'd end up with negative 2i, 3 minus 5, and 4 minus a negative 2. So that would be plus 6i, 6j. So that would be the difference. The resultant is the addition of the two vectors, whereas this difference is sometimes useful. Not as much, but every once in a while. And then you could call that, well, you just have to call it a different name. Resultant would not be appropriate. So we could just call it V sub C for whatever reason. Now, C is not a good one either. Let's just call it V3. V3 is the difference between the two vectors. And you can find the magnitude and the direction. I forgot to do the direction here. Did I? No. I did here. No, I didn't. So these are the angles of the original one. So if I wanted the angle of the resultant vector, it would be the inverse tangent of 2 over 8. Okay, so that is basically what's going on here. Let's kind of summarize this whole thing again. So, one-dimensional motion, you're given x as a function of time. You can find the instantaneous velocities and accelerations by taking the derivatives. If you want to find the average velocity, you take the difference in the position from the end to the beginning and divide by the time. So if I ask for average velocity, do it this way, not this way. In two dimensions, it's similar, except you can either show it as two components or you can put it into a single position vector. And to find the velocity and acceleration, you just take the derivatives of each component with respect to time. 1 time to get the velocity and 2 times to get the acceleration. So I did that example for you. Going the other direction, in one-dimensional motion, I can give you the acceleration as a function of time. And you can use integration to find the velocity and position, but you do need these initial conditions. In 2 dimensions, again, you can use this unit vector notation, and you integrate each one separately. You would need 2 initial velocity conditions and 2 initial position to be able to find the particular solution when you integrate these, and they'll just be polynomials, so you know how to do that. Okay, what else was there? If I ask for magnitude and direction, the magnitude is the square, sum of the squares of the components times the square root, and the angle is the y component over the x component, inverse tangent. Know how to do a cross product, A cross B or R cross F, using this determinant notation. Able to calculate in 1 dimension the work where the force is a function of distance. Now, one interesting thing is we kind of alluded to this earlier. What do you do if it's a function of time? And it actually involves parametric equations. So here, it's a function of x. if you have x as a function of time, and what would happen is not that you have force as a function of time and position as a function of time, then you'd have to, they're both functions of time. So there's some way mathematically of doing that, but in our case, I'm going to give you force as a function of displacement of distance, so that it's just a simple polynomial integration and then evaluated at the ends to get the definite integral. And then just some simple vector addition using unit vector notation, and find the magnitudes and directions of vectors based on the components, and find the resultant by adding the two components together, and then finding the magnitude and direction of the resultant vector, or subtraction of the vectors. So hopefully that gives you a better idea what's going on.